Greetings, traveler. I'm the Calculus Cleric, and today we'll be working with infinite series. So the specific question is to find the sum of 1 over 1 multiplied by 3 plus 1 over 3 multiplied by 5 plus 1 over 5 multiplied by 7 plus and so on and so on. This, basically, the ellipsis is telling us this pattern continues. So I just dropped a hint. What we're going to do is be finding a pattern. Now, our first instinct might be to multiply this up and attempt to find the pattern from there, but first we need to pause. Why would they give us these numbers in this format with 1 over 1 multiplied by 3 when they could have just given us 1 over 3? They're clearly trying to tell us something. So these little hints in the question will help you go a long way. So when you analyze the relationship between the first terms of the sum and the second terms of the sum, you notice that they will have their similarities. So first terms first. So 1 and 3, 2n minus 1 and 2n plus 1. So both of them are multiplied by 2, but in one of them there's a 1 subtracted, in the other one there's a 1 added. So if you take a look at this, so there's a 1 here, plug 1 in there, which is 2n, which is 2, 1, and that's 1 here. And then you get the second term, 2, 2, 4. 4 minus 1 is 3. And then third term, 3, 2, 6, 5. And then second one, 1 by 2 is 2. 2 plus 1 is 3. 2 by 2 is 4. 4 plus 1 is 5. And then 2 multiplied by 3 is 6. 6 plus 1 is 7. So this formula works. And now we can do partial fraction decomposition, otherwise we'll just end up getting that again. Multiply both sides out by 2n negative 1 multiplied by 2n plus 1. Remember, when you finally plug back the a and b values, do not swap the bases. Okay, so the first one. Normally I cancel out the b and solve for a first. So what plugged into n will make b 0? 1 half. So let n equals 1 half. It's 1. 1 minus 1 is 0. Okay, that's 1 half. 1 plus 1. Okay, so our a value is equal to 1 half. Now for our b value, what can we do to cancel out a? Well, we can make this negative. Yeah, and then 1 half that. Okay, so let n equals negative 1 half. So that'll cancel out a, because negative 1 half multiplied by 2 is negative 1, plus 1 is 0. So that's 0, and then plug that into b, negative 1 half, which is negative 1, negative 1, negative 2. This is equal to negative 1 half, so b is equal to negative 1 half. Okay, and plugging it back into the a and b values, we get this, which is equal to that. And so that's our partial fraction decomposition. So we split up the two terms on the bottom into two separate fractions. And now from here, we can go out and evaluate the sums, and hopefully we might get some terms to go and cancel each other out. So plugging in 1 into this whole thing, 1 over 4, 1, 4, 4, 3, 2, 1 half, minus 1 over 1, 4, 5, 6. And then we add a 1 over 2, 4, 2, 8, 8, 7, 6, negative 1 over 4, 2, 8, 9, 10. So that's our second one. So you notice things are already canceling out. See that negative 1, 6 and the positive 1, 6? So that's gone, leaving us only this. I'm just going to test one more just to be sure. One over 4, 3, 12, minus 2 is 10. Negative 1 over 3, 4, 12, plus 2 is 14. So 1 over 10 cancels out because 1 over 10, negative 1 over 10 is 0. And if you notice from these terms, I'm not summing them up together because I don't want to add the fractions together. You notice that they all start with a 1 half. So that's going to be a consistent thing in our general S of n sum. So S of n is just like a general term for all sums. So if I were to plug in a random number into n, it will come out to the generated sum. Like when I plug in 2, it'll come out to the exact same sum that the degree 2 is. But it just represents any of these numbers. So it obviously starts with the 1 half. Now we got to go find the pattern between each of them. So 6 plus 4 is 10. Okay, it's a negative. So though it might be tempting to make them to attempt to find the pattern based on their respective steps. So like this one should be plus 4, and then this is plus 4 and plus 4 and so on. But we can't get 1 over 6 from straight from the n term 1, and our general term is in terms of n. So we have to find something that makes n work. 4n plus 2 does the job. So 1, 4, 5, 6, 2, 4, 2, 8, 9, 10, and so on. And a cool trick with this is that if you notice 4n plus 2 is also the second half of our partial fraction term. So the term that does not stay constant is the one that's normally subtracted from the rest of the sum. So when it comes out into a format like this with a constant and then some general term, that general term will almost always be the second part of the partial fraction that you generated. I normally just attempt to plug that in and see if it works. If it doesn't, then do something else, but that's my go-to method. Now, we have our S of n, which is our general term, and basically to find the whole complete sum, a rule tells us if we take the limit as n approaches infinity of S of n, then we'll find the answer to our sum for n plus 2. Take the limit of infinity of that, so that's 1 half, and then the bottom, this will be 1 over infinity, so that's 0. So our final sum is 1 half.